So for 3.5, we have exponential and logarithmic models. So in this one, we are just really going to start looking at models for different sets of data where we would use either an exponential function or a logarithmic function. And then moving on into 3.6, we'll use our calculators more to probably help us calculate this. So this section is more algebra based. Section 3.6 will be more calculator based. So we have several different types of models. We have the exponential growth and decay. We have the Gaussian model, which we're not going to touch on that a whole lot. But then we do have the logistic models and the logarithmic models. And your calculator for 1, 2, 4, and 5, your calculator actually has a regression model for those. So you could plug in data points and find a regression model for any of those types of models. These are graphs of what the different models look like. So you have your exponential growth and decay. We've talked about those. The Gaussian model, that's kind of your bell curve that you hear about a lot. The logistic growth tends to be a population model where it grows really quickly at the beginning and then it levels off. And then we just have our log and our natural log models. Those are your log and your natural log graphs. So this section, we're just going to go through a few examples here on how we could use these different models. So for example 1, we have a table of values, and then we have the plots pointed for those values, and this is the revenue for Amazon from 2011 to 2016. We are given this exponential growth model right here, the 5.3e to the 0.2016t. And the question is, according to the model, when will the revenues hit 300 billion? So if we were going to solve this algebraically, what we're going to do is we want revenue to equal 300. So in for the R, we would plug in a 300 and then set that equal to the 5.3e to the 0.2016t. All right? And then we'll use our solving skills that we learned in the last section where we could divide both sides by 5.3. Right? And if you do 300 divided by 5.3, you get a decimal that doesn't really end. So we're just going to leave it as the fraction. So we have 300 divided by 5.3 equals e to the 0.2016t. So from this point, we could take the natural log of both sides. So we would have the natural log of 300 over 5.3 equals 0.2016t. No, it's not letting me cross my t. So divide by 0.2016. And when you do the natural log of 300 over 5.3 divided by 0.2016, we get that t is about 20, right? And in this case, if you look at t in your graph, they show you that t is in terms of years. For the next one, we are going to actually find our own exponential function, but we're going to really kind of be given 2 points. So the first one, we're talking about fruit flies increasing according to the law of exponential growth. So we have after 2 days, there are 100 flies. So we could think about that 2 days is like our x value, 100 is our y value. And after 4 days, there are 300 flies. Okay. And so remember that if you went back to your previous slide, so remember back from our previous slide when we had all our different growth models, this is going to be exponential growth. So we're using the model y equals a e to the bx, right? So in this case, we have these x and y values. So what we're going to do is we're going to actually set up 2 different equations where we're subbing in. So our first one, if we sub 100 in for y, we have a e to the 2b because we substituted 2 in for x. We could do the same thing here. We could say 300 equals a e to the 4b. So then the next step is we actually have to solve for our a and our b. So what we're going to do is it's kind of like when we solve systems of equations, we're going to divide these two equations. So we're going to say if 300 equals ae to the 4b, then in a way it's like we're setting up this ratio of 100 would equal ae to the 2b. Okay? And if we start simplifying, if we simplify the 300 over 100, we get 3. Our a's simplify. And then if we have e to the 4b over e to the 2b, that leaves us with e to the 2b. So now we just have b to solve for. We can take the natural log of both sides. So we get 2b times the natural log of e, which is just 1. So we get the natural log of 3 equals 2b. So b equals the natural log of 3 divided by 2, right? And now we can go back into one of our equations. I'm going to go back into this first one here, and I'm going to plug in that value for b so I can solve for a. So I'm going to say 100 equals a e to the 2 times natural log of 3 over 2. The nice thing here is those 2's could simplify. So we get 100 equals a e to the natural log of 3. Well, e to the natural log of 3 is just a number, so we can actually divide by e to the natural log of 3 and divide by e to the natural log of 3. Or you may even notice that e to the natural log of 3 is really just simplifying, could simplify down to be 3. So when you do this division, you get 33.3 repeating equals your a value. So our equation, now that we have b and we have a, you could actually write out your equation of y equals a. So we'll say 33.33 e to the b, so the natural log of 3 over 2 times x. So we've come up with the equation, and the question is how many after 5 days? And so now we actually have to substitute 5 in for that x value. So we have e to the natural log of 3 over 2 times 5. And when you go through and you calculate that, you end up getting about 520 flies. On our next problem, this carbon dating problem, this is some information that the book gives us in terms of carbon dating, where they tell us that the model for carbon dating is that R equals the 1 over 10 to the 12 e to the negative t over 82,223. Okay, and so they want us to estimate the age of the fossil. So find our t value when they give us the r value of 1 over 10 to the 13th. So we need to substitute this in for the r value. So if we have 1 over 10 to the 13th equals 1 over 10 to the 12th, e to the negative t over 8,223. To get rid of 1 over 10 to the 12th, we could multiply both sides by 10 to the 12th. Right, and 10 to the 12th over 10 to the 13th really just leaves us with 1/10 e to the negative t over 8,223. And so now we've set it up that we could take the natural log of both sides. That would bring this whole quantity down. So we have the natural log of 1/10. The natural log of e is 1, so we're just left with negative t over 8,223. You could multiply both sides by 8,223. Right? And when you multiply both sides by 8,223, you get negative 18,924. But that equals negative t. And so then when you divide both sides by a negative, we get that the fossil is about 18,924 years old. Probably need an S on my years. And then the last example is the spread of a virus. So on a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. The spread of the virus is given by this model right here in that equation, where Y is the total number of students infected after T days. College will cancel classes when 40% or more of students are infected. So the first part is how many students are infected after 5 days. So after 5 days, we need to plug in a 5 for T. So we would say Y equals 5,000 divided by 1 plus 4,999 e to the negative 0.8 times 5. And then when you actually calculate that, you get about 54 students. And then the second one says, after how many days will the college cancel classes? And so we know when 40% or more of the students. So we first have to figure out what's 40% of 5,000, right? And 40% of 5,000 is 2,000 students. So when 2,000 students contract the disease, so that means that's what we're plugging in for this Y value. So we would say when 2,000 equals 5,000 over 1 plus 4,999 e to the negative 0.8 t, and we have to solve for t. So we're going to have to multiply both sides by this denominator, so by the 1 plus 4,999 e to the negative 0.8 t. Multiply that over here on this side too. Right. And then we could distribute, so that will simplify that. We can distribute our 2,000 into that. So we get, actually, let's not distribute. Oops, sorry. Let's go back on that. We're not going to distribute. So when we have this 1 plus 4,999 e to the negative 0.8 t times 2,000 has to equal 5,000. Let's divide both sides by 2,000. Sorry, that's not showing up. And so if we do that, we get 1 plus 4,999 e to the negative 0.8 t equals equals 2.5. We could subtract 1 from both sides. So I'm going to go over here. So now I have 4,999 e to the negative 0.8 t equals 1.5. Divide by 4,999. So you get e to the negative 0.8 t equals 1.5 over 4,999. Sorry, I'm running out of space here. Okay, I'm just going to go down to this next little part of this next slide. So from here, I can take the natural log of both sides, which brings that negative 0.8 t down to the front. Natural log of e equals the natural log of 1.5 over 49.99. Right, that's just 1. So I can divide by negative 0.8. And so I end up with t equals 10.14. So after just over 10 days, they'll have 40% of the students exposed, and they would end up shutting down the campus.